Hey there, this is going to be lesson 2C-1, and we are going to talk about the inverse of exponential functions and formally introduce you to a logarithmic function and what that looks like. So, you'll be successful if you can understand the relationship, again, between the inputs and output values for exponentials and logarithmic functions. If you can create a table of values for exponential and logarithmic functions and understand how they're related, as well as change from exponential form to logarithmic form and vice versa. So, I want to go ahead and remind you that an exponential function has the form y equals a times b to the power of x, where b must be greater than 0 and 1. Remember that a here, this is your initial value where you're starting, and your b value is going to be your base. Outputs will change proportionally, meaning they're multiplying, right? They're going to grow. And if I have a axis here, and here's my initial value, you'll notice that the outputs grow proportionally, right? This is like the amount of COVID cases, the amount of zombies, the amount of likes on a viral video, so on and so forth, over consecutive equal length input value intervals, okay? So the outputs are changing proportionally, multiplying by a certain value, and the inputs will have equal length input value intervals, usually adding by a certain amount. A logarithmic function, because inputs and outputs switch, will reverse this. Logarithms will have the form y equals a times log base b of x, where b must be greater than 0 and b cannot be equal to 1. It's also important to note here that your domain has to be positive. Domain must be greater than 0. And I'm going to go ahead and add that in right here. I'm going to say domain x must be greater than 0. It cannot be 0 and it cannot be negative. Whoop, I wrote that in the wrong spot. Okay, that's for logarithms. So domain must be greater than 0. Greater than 0. Okay, and again, since we're switching, now our inputs will change proportionally. We'll look at that here in a second, and our outputs will have equal length intervals. Kind of a switch. It's the first time our outputs are equal length, okay? So again, remember that if I have a function f that has the input-output pair a comma b, then the inverse of f is denoted f inverse and will contain input-output pairs b comma a, where they switch. The functions will be reversed or reflected over the line y equals x, our identity function. And if I have an exponential function b to the power of x, the inverse is going to be log base b of x. So let's go ahead and see how we can drum up the logarithmic function. The table of values of the exponential function f of x equals 2 to the power of x for selected values of x is in the table. The figure gives the graph of f. So we have y equals 2 to the power of x right here, okay, and they call this f. We want to go ahead and complete the table for the inverse. Well, this is pretty easy. My inputs and outputs are going to switch. So 1 half negative 1, 1 comma 0, 2 comma 1, 4 comma 2, and 8 comma 3. And so we're going to go ahead and graph these, and this inverse will be log base 2 of x. Again, the base stays the same. So, and when I graph this, I'm going to go ahead and graph my reflection line, the identity function, just so you can kind of see, again, that reflection. And so our inverse, 1 half negative 1, 1, 0, 2, 1, 4, 2, and 8, 3. And so this graph is going to look like this. And here is generally what a logarithmic function looks like, okay? You're going to have a vertical asymptote at x equals 0, again, unless you have a shift. Let's go ahead and note that. We have a vertical asymptote at x equals 0, or if we're doing translations, it'll be your h value, whatever h is, that may shift. And again, I want you to notice how the inputs are changing, right? My input is growing proportionally or multiplying. 1 half, 1, 2, 4, 8. So I must multiply by this base before I can increase my outputs by one integer, right? I had to multiply 1/2 by 2 in order to get it to grow 1 unit. Now I have to multiply by 2 again to get it to grow 1 unit. Get it multiply by 2. Now it's at 2. Multiply by 2. Now it's at 3. So our inputs are growing proportionally, multiplying by 2, and our outputs are increasing over equal length intervals, adding by 1. Okay, so the other thing we want to talk about is the end behavior. A logarithmic function, again, since it has a vertical asymptote, it will approach the value of the vertical asymptote on one side. It'll get arbitrarily close to it, and then it will approach negative infinity on this side. And as our x values approach positive infinity, the output values will increase unbounded towards positive infinity. So let's go ahead and look at some limit notation for logarithms. Determine the behavior of f inverse as x becomes arbitrarily close to 0. Write your answer using limit notation. So this is going to say, what is the limit? Again, my function here is f inverse of x as x becomes arbitrarily close to 0. And I want to be proper here. Since I'm coming from the right side of 0, I'm going to put a plus on this. Okay. And that value is going to negative infinity. Negative infinity. E, determine the behavior of f inverse as x increases without bound. Okay, so when we increase without bound, that is going to be x approaching positive infinity. And for our function here, we have positive infinity. Now, you could get some variations on this if you multiply by a negative a value, where you'll get a vertical reflection, or you could have a negative multiplier on your argument on the inside, which would cause a horizontal reflection, or vice versa. Okay. So here we go. We're going to go ahead and answer some questions here. They say the function g is given by g of x equals 3 to the power of x. Which of the following expressions defines g inverse? Take a second, identify what's the inverse of 3 to the power of x. Okay, hopefully you did not take too long on this. It's going to be a logarithm function with the same base. So log base 3 of x. Next one, the function h is defined by h of c equals log base r of c. Which of the following expressions defines h inverse of c? Okay, again, hopefully you didn't take too long on this one. Again, the inverse of a logarithm is an exponential function. So we have base r. It's going to be log base r. Okay, answer is A. I don't like how they use the same input value here, c. They're just using, I guess, c. I would like to see x there. But anyway, it's r to the power c. The base stays the same, moral of the story. Okay, next, we're going to go ahead and look at some exponential functions here. And k is given. Which of the following could be the inverse of k? What is the inverse of k? Go ahead, pause this, and I'll show you the answer here in a second. Okay, how I would approach this is I would get values here for my function for k. So 0, 1. The next one looks to be 1, 3. And what that tells me is that this is the exponential function 3 to the power of x. 3 to the power of x. So the inverse function of k is going to be log base 3. So I'm looking for my inputs to be growing proportionally. Inputs, because they switch. So it's not going to be A. It's not going to be B. And, okay, so C, I have proportional inputs that are growing. But this is kind of weird. Notice how these values are switched. I really wish it would be like 981 would be 2, 4, which seems to be our answer here. 8, 4, 64. So that should be a 2. 64, 2. So answer here is going to be D. D is y equals log base 3 of x, the inverse, okay? You go ahead and multiply the inputs in order to gain an output. And obviously there's a value missing in here. 27 would give you 3. Okay, another practice one. Here is the function d is given d of x equals log base 4 of x. Which of the following could be the graph of the inverse, d inverse? Take a second, try this one. Okay, log base 4, this has your inputs growing proportionally by 4. So I just want to go ahead and for sakes and purposes, I want to show you A. This is log base 4 of x. So all logarithms will generally have this point unless there's a shift, 1 comma 0, and then they're going to multiply by 4 in order to grow 1, right? Or multiply by b, whatever that base is, to grow 1. So we want the inverse of this, and pretty straightforward, a reflection of this would give us our function. So the inverse, d inverse, again, is going to be an exponential 4 to the power of x. So pretty straightforward. Hopefully you got b. B is your answer there. Okay. Let's talk about the last idea here in this lesson, which is a fairly common question on the AP exam. You'll see it generally on multiple choice or on FRQ, almost guaranteed. And now we have the full gamut of functions that you're going to see on the AP exam for this question. We're given a table of values, and they say let g be an increasing function defined for x is greater than 0. The table of values of g of x at selected values of x. Use the table of values of g of x to determine if g is best modeled by a linear, a quadratic, an exponential, or a logarithmic function. So the first question here, A, if this is an FRQ question, is just identify this function. And so what I like to do, one is I like to see, okay, are my inputs or outputs multiplying? And generally you can see a pattern. And in this case, yes, I am multiplying by 3 every single time. Here, multiplying by 3. Okay, and my inputs, it looks like, are adding by 2. So this is going to be a logarithmic function. And then on part B, they want you to give a reason, a relationship based upon the change in output values of G and the change in the input values of G. And I think this wording needs to be updated. It should say refer to values in the table for your explanation. College Board has beefed this question up in terms of explanation over the past couple of years of implementing this course. So let's go ahead and kind of look and see what we have here. So our reason for this is we can say the input values are changing proportionally. Proportionally. And then in parentheses, before I proceed, I'm going to go ahead and like give an example. I'm going to say by a ratio of 3. So I'm going to say also here, for example, 3 divided by 1 is equal to 9 divided by 3, which is equal to 27 divided by 9, which is equal to 81 divided by 27. Okay, College Board has asked for an example of this pattern, so they want you to refer to the values, and so I'm showing that there is a continuous ratio here of 3. Okay, and I just put that in. I know it's a pain in the butt, but it's pretty easy, and that just shows that, hey, all my ratios are 3. And then now I'm going to talk about my output values. While the output values Or you could say over, I don't know, well, if output values are increasing by 2. Or in parentheses here, I'm going to say adding by 2. Okay. Another way to explain this, you could say over equal length output value intervals. I kind of do like that, over equal length output values. I'll show that wording here in the next one, and then in parentheses say adding by 2. So always refer. College Board has been very specific. They want to see the math in your explanation. Okay. So a couple of practice problems here. Go ahead, look at this one, and then I'll show you the answer. So identify the function. Try to drum up a reason, and I'll show you my reason here in a second. Okay, hopefully you identified this as an exponential function. The output values are multiplying by 4. So our justification is that the output values are increasing proportionally, multiplying by 4. For example, and I went ahead and I showed this ratio, 16 over 4, which is equal to 64 over 16, which is equal to 256 over 64. So whenever you use that justification proportionally, it's a good idea to go ahead and show that ratio. And remember, the ratio is always any term divided by the term before it. And if you're ever confused, just go to the simplest example to try to justify that relationship in your mind. Like I'm multiplying by 4, I can see that, but how does a ratio look? Well, which one would give me 4? Is it 4 over 16, or is it 16 over 4? Right, just to help you kind of justify that, right? So 16 over 4, that's going to be equal to 4, and then I just keep that pattern going. Over equal length input value intervals. So here's e-livy, and I specifically say adding by 1. I add that. College Board is being picky about that, okay? All right, here is the next practice one. So go ahead, pause me, identify this function, and then give a reason based upon the change in output values and the change in input values. All right, here we go. We have a logarithmic function. Hopefully you notice those input values are multiplying. And so our justification is the input values are increasing proportionally, multiplying by 5. And for example, 25 over 5 is equal to 125 over 25 equals 625 over 125. While the output values have equal length intervals. And I put adding by 4. There you go. All right, hopefully in this video you learned about a logarithmic function, the inverse of an exponential function. Hopefully you know the relationship between them and how to change between the two forms, as well as justify what makes a logarithmic function. Go ahead, give me a thumbs up, like the video. I'll see you in the next one.